Okay, let's talk about polar double integrals. So far we discussed double integrals, but only in x, y, z coordinates. So let's talk about two-dimensional integrals to begin with. So that is, we're dealing with a function of two variables. And usually we look at the integrals over rectangles or maybe over some more complicated domains, but still we tend to stick to domains of type 1 or domains of type 2. Do you remember what these are? Try to formulate, pause the video if you forgot. What exactly is domain of type 1? What exactly is domain of type 2? But sometimes we would look at the domains which have some kind of circular symmetry. For instance, something like that, maybe semi-annulus on the right or just a simple disk on the left. And make sure if you agree or if you can reproduce even without looking at those descriptions below. Does it make sense that they're described like that? And in those cases, especially for the second one, for the one on the right, you cannot express it as a domain of type 1 or domain of type 2. It's neither. Of course, you can make up this region from the several domains of type 1, type 2. But it would be nicer to kind of use a single approach to it so that we end up with a single integral rather than several pieces. Can we take the integral over such region in one piece? So for that, we should be able to express it in one piece. And look, if we write it in terms of the polar coordinates here, then what we see is actually not that different from a rectangle in rectangular coordinates, because a rectangle in Cartesian coordinates is described like this. A comes from, x goes from A to B and y between C and D. So that's the Cartesian rectangle. But since we are we are limiting our variables r and theta, polar variables, by fixed limits, then we will refer to this as a polar rectangle in both cases. This is also a polar rectangle. We don't even have to come up with any intervals type 1 or type 2 with variable limits representing functions. Here we have constant fixed limits, and that will be our polar rectangles. We'll find out that double integrals will go very easily in terms of these polar rectangles. Good. But exactly how? Well, rather than doing our standard thing, subdividing according to the rectangular grid, let's do something smarter here and subdivide using the polar grid, which goes like that. Theta goes from 0 to 2 pi, etc. And then we go radially like that. So we'll get our typical pieces, our typical bits. They don't even look like rectangles, but they look like sectors of a circle, or maybe pieces inside those sectors. But since they will vary between fixed theta, say going from alpha to beta, and this goes between R1 and R2, all constant. Then we'll refer to them as polar rectangles as well. They will be all polar rectangles. And so these are basics of polar coordinates. Review is needed, but that will be the typical shape that we'll work with here. Today, polar rectangle. So it turns out that we could write similar Riemann sums f of x I sub j and f stars del A over these polar rectangles, where del A would be the area of this polar rectangle. So the key part becomes finding the area of this polar rectangle. How do we go about it? So for that, maybe it's a good idea to remember the area of the polar sector. So what would be the area of the entire sector if we go like this? Area of the sector. So try to figure it out. Pause the video and try to figure it out. And see if we get this result. 1/2 r squared theta. And theta here will be, I guess, del theta. In this case, beta minus alpha. So see if we can prove it. Question is why. The hint, of course, you work with the piece of the pie, and this piece of the pie is determined by delta theta. And since you know the area of the entire pie, this area of the sector will be the same ratio of the entire pie as this angle over the entire circumference of the entire 2 pi, the total circumference of the circle. So that's the hint, but try and figure it out. So then to understand, maybe let's go back right here and understand now the area of the polar rectangle, which lasts like this between A and B. So then we will take, so area of R will be the difference between the outside sector and the inside sector. Inside sector we can cover in blue. So what is the outside sector? It's 1/2 r squared, in this case b squared, del theta, minus 1/2 inside sector is the blue one, a squared del theta. But del theta and 1/2 are the same. Why don't we take them out? We'll have b squared minus a squared del theta. So then we can write it as 1/2 b minus a, b plus a del theta. So what do we get here? We can simplify. B minus a will be this distance, del r. Why don't we call it del r? So we'll get b minus a will be delta r, then b plus a in this 1/2. Why don't we combine it to get b plus a over 2, and then del theta. So b plus a over 2 is like a radius somewhere in the middle. Is there? Well, maybe call it r bar for the average of A and B. And so we'll have r bar times del r del theta. So that's the key formula to remember, and maybe even without bar. So you can find some radius in between two given ones, that the area of this polar rectangle is just r del theta, roughly. And that will be the key moment to understand here. So for instance, if your del r is very tiny, if this, we're trying to figure out that elementary area, assuming that this is maybe infinitesimally small dr, then we can say that dA, which will end up in our integral, will be approximately r dr d theta. So now it's clear what will happen with our double integral. All we have to do is convert to polar coordinates by converting xy to polar. Well, x is r cosine theta, y is r sine theta. And as far as dA, you have to write that. Don't forget r. Okay, that's it. Pretty much if you have this recipe, then you can manipulate. This is the discussion of why it works, but I already showed you there's nothing new here. Maybe notation is slightly different. If you have this recipe, then you can convert any integral to polar coordinates. How do you know if you should? Well, look at the region. If the region has some kind of rotational symmetry, then it's ripe for conversion. And that's the rule. So if you are integrating over this polar rectangle, you will convert this region to this double integral. But sometimes you can even integrate over more complicated regions. So again, here is the quick and dirty understanding of why dA is like that. Well, remember what is the length of the arc in the circle. If the arc is spanned by d theta, it's the radius of the circle times that d theta. So this part is r d theta. The other part is dr. So even though it's not exactly a rectangle, it's kind of curved rectangle. It's different from that so little that we can say approximately dA will be r dr d theta. So that's kind of a quick and dirty way to remember why you have this r sticking inside the integral. So here's an example. Shall we do it? R is the region in the upper half plane bounded by these two circles. So you have this semi-annulus, radius 1 and radius 2, and only in the upper half plane. That's the region. So a good idea to sketch and also good idea to describe it. So R goes between what and what? 1 and 2, right? And theta between 0 and pi. Okay, then we're all set. We can convert it into polar region into polar integral by writing r dr d theta instead of dA. Instead of x, we will write r cosine theta. Instead of y, r sine theta. Don't forget to square. That is the function multiplied by dA and integrate. It doesn't matter in which order. Again, Frobenius theorem apply here that we can do repeated integral as long as the bounds are constant, then it doesn't matter in which order. So if we are doing dr first with respect to r, that means that we're integrating how? Along the circular tangential direction. So then let's do that. So we want to integrate first with respect to r. Let's simplify a little bit. And so r will last between, oh no, wait a second. If we are doing with respect to r first, then of course what I drawn is the theta direction. So we have to do the integral with respect to r first. That means r goes between 1 and 2. And then with respect to theta between 0 and pi. Hopefully it makes sense. Hopefully you caught my mistake. Okay, so let's simplify. So first we can multiply by r throughout. So we'll have double integral. We'll have 3r squared cosine theta plus 4r cubed sine squared theta. Integrated with respect to r from 1 to 2. And then with respect to theta from 0 to pi. Integration with respect to r is pretty easy. So we'll have r cubed over 3. So we'll just get r cubed here from 1 to 2 cosine theta. So still integral with respect to theta remains. Plus r fourth over 4. So we'll just get r fourth. And again from 1 to 2. Sine squared, how can we simplify that? Maybe use the double angle formula. Is it 1 minus cosine of 2 theta over 2? I don't remember. So I will remind myself that cosine squared minus cosine squared theta minus sine squared theta is cosine of the double argument. So if I'm interested in sine squared, I will convert everything to sine squared, 1 minus 2 sine squared theta. So indeed, I will get this formula. Sine squared is 1 minus cosine 2 theta over 2 good. That has to be integrated with respect to theta. So then I will be left with 2 cube is 8, 1 cube is 1, so I'll get 7 cosine theta, plus here similar logic, we'll get 16 minus 1, 15 halves, 1 minus cosine 2 theta, d theta. So I will get 7 sine theta from 0 to pi, which will give me 0, plus 15 halves. Integral of 1 will just give me pi, and here we'll get sine 2 theta divided by 2 from 0 to pi. And again, it will give 0 on both ends. So what are we left with? Just 15 pi over 2. That should be it. Let's clear and check. So not only you draw the region here, sketch the region, but also make sure you write the description. And then that makes it easy to set up the integral. Setting up the integral is half of the job. You'll get half credit just for this correct expression. Then you will simplify, integrate one by one, and get the result, 15 pi over 2. And these are the integrals in polar coordinates of rectangles. Of course, we can then graduate to integrals of type 1, integrals of type 2. So that's one of those when we get to look at the variable rather than saying top and bottom, as you do with respect to y, or left and right, as you do with respect to x, you will say inside and outside. When you're talking about polar, here you have a definite inside and outside. Limits on your region are as function of theta. And here's another r as function of theta. And that means that first you'll be integrating with respect to r. So the question for you is, if you had the region which looks like that, theta is a function of r, and theta is a function of r here as well. But okay, maybe let's come up with different, maybe I don't know, alpha of r and beta of r. Then how would you write your double integral over this region? Practice, and we'll discuss in class. Good. That's all for now.